Hey, if I am audible, could you please people? Hello everyone. If I am audible, could you please people ping here that I'm audible in the comment box? Hey, if I am audible, I think from my end I'm able to see that from my end all the mic and everything is working. So let me start and initiate today's session. So today's session is basically based on what LLVM is. So get start. If you have gone through the LLVM documentation another place, then you may have some understanding regarding LLVM. And if you have seen the LLVM website, then from there you are aware that, or you may be knowing that what LLVM stand for. Its abbreviation is low level virtual machine. But LLVM is not just a low level virtual machine, but it's more than that. So what LLVM is basically we are going to discuss about here. Um, when we talk here about the compilers, then if you see the compiler's main role is what? It converts your source code to the binary, or you can say in more logically correct way, it take .i as the input and it generate .s file. This is the complete role of the compiler. So during this phase, we do lot of things like we optimize, we analyze the code, and we try to optimize on the basis of initially people were only concerned about performance, but now people are also caring about what? Power. So why I'm talking about here is this because so that you can get a broader picture about the compiler domain. But still, this talk doesn't relevant to the what compiler or what LLVM is. So let's start. When I'm saying what LLVM is, so it's not just a project to build a compiler. It's more than that. So let's initiate our talk. When we think about talk about LLVM, then we first think about is LLVM is a compiler? No, it's not. Then what is a LLVM? LLVM is a framework. That's correct. So what that framework is designed to be? So that framework is work is very simple. It is designed to analyze, optimize, and transform your whole code into best available format or best available for the machine during throughout its program lifetime. So in simple way, if I want to say what LLVM is, then when we say LLVM, we are talking about a project and a tool provided by the compilers. So earlier every companies and university were building their own compiler from the scratch. Each compiler used to have their own IR, their own optimizer, their own backend. Then they have to what have to do redundant work multiple times. This means we are repeating the same work again and again. Let us suppose there are two people. I am also writing loop unrolling pass for my compiler. You are also writing loop unrolling pass for your compiler, and different location and different place. So it's redundant work, right? I am adding. But if you can comment whether I'm audible or not, it will be. Hey, yes, you are audible. Okay. So basically, when I'm talking about, we do a lot of redundant work. When I'm talking about loop optimization, it's algorithm compiler used to optimize our loop in a source code. And let us suppose I am creating a new backend, then what that backend is about. So when I'm talking here about, let us suppose there are two person A and B. They are creating a there are two person A and B, they are creating compiler from scratch. So whatever A is doing, the similar work B be doing, so that every time A is writing parsing algorithm, B is also writing parsing algorithm. New hardware is coming, A is giving support to the new hardware, and similarly B is also giving support to the new hardware. So all these are redundant work, and they not be the best. Maybe the A is working, A is using good algorithm for loop unrolling, but he's not using that much great algorithm for other optimization. Similarly goes to the B. Now think of A and B as two companies. So different company may have different approach for the solution. So each solution may not be optimal for each case. So let us suppose A want to optimize, do the inlining. So the heuristic A is using, maybe not B understand it, but B have better inlining code than A. So there was also not good understanding of the compiler during that time. So all these things led to the what, redundant work every time. And this redundant work uh, leads to what, need to redo multiple things, which leads to what, your, even though your code look optimized, but every place you are doing the same work. That's where LLVM comes and it changed the things. So LLVM just said, let's build a common infra for everything. Instead of depending on uh, property related things, you are doing the same thing, I'm doing the same thing, let's build a common infra for that. Now the same language can share the same backend and the same compiler optimization. That's why today many compilers are based on LLVM. So when I'm talking here about, if you see from the terminal what I'm saying, what is LLVM? LLVM is a compiler framework designed to enable analysis and optimization throughout the program lifetime. Now in your mind, the question should be there, what does it mean by program lifetime? What is program lifetime? So let's understand what program lifetime means. If even LLVM is saying that program lifetime, what happened? LLVM, instead of directly converting your source code into binary, in middle it convert into a LLVM IR. That LLVM IR is where everything fancy related things of optimization, analysis, and transformation of the LLVM happens. So when LLVM say program lifetime, so it simply means that it does not just run once and finishes its job. Along with that, it's a system that keep understanding and improving a program through its life, including, so when we talk about program life, so when it comes, so from preprocessor we get .i file, from .i file we convert it to compile it and generate .s file, and from that .s file we again convert it to .o file, and from .o file we get a .exe file. So during linking, compiling, and running, and even the situation when program is ideal, what does LLVM try to analyze is, so this is all four things is called as program life. Program life means, from here doesn't mean execution, I'm not talking here about execution. So program life in LLVM term is means mainly when how the compiler is translating it to exe, and in between what all transformation it is doing. So basically all the transformation of the LLVM is done on IR. So during phase compiling, linking, and running. When I say running here, I mostly mean PGO type optimization, which I will show you in upcoming lectures. So that here about LLVM I mean. And also when I talk here about the entire period during which the program exists in LLVM IR form and still can be analyzed or transformed is called as LLVM IR. So before LLVM, how was the flow? Let's check. And after LLVM, how the things get changed. So before LLVM, let's see what is the flow. So when I'm talking about before LLVM, then basically what is the flow is simple. If you see every time, if you see that, if you have not seen my previous video, you can see whatever I have discussed there. Mostly they are toolchain, how flow. That's all describing before LLVM how is the flow. When I'm talking about before LLVM, then let us suppose we have a C source code. Let me change the color that it is more visible. We have a C source code, then we take a .i file as, then preprocessor work is to generate .i file, then .i file we get what? We get .s file. Here the compiler comes where we are more interested in how it works, and then from .s file we get .o file, and from .o file linker comes and we get .exe. So compiler were generating intermediate file every time. Let us suppose here it used to this all the intermediate file generated by the compiler at each stage, and they were not used much internally, and they were get deleted. So if you see a new language I am writing, then I again have to, let us suppose I have a, this is my compiler where I have a support for x86 language for the C language. Now let us suppose a new frontend is coming as C++. This frontend, again I have to write the parsing algorithm for the C++, and again it will convert it. Let me clear this. So let us suppose we have a C compiler and its work is C2, we are converting to x86. What we are converting to x86 binaries. Now let us suppose a new frontend is coming at C++, then we have to again write complete compiler from scratch to x86. So again a new back coding language is coming as Objective C, then we have to again write complete for x86. So if you see how many compiler we have written, 1 2 3, so total 3 compiler we have written. Now let us suppose if I have will change here one more backend. Let us suppose now I want to create back for, now let us suppose we want to also create for a new backend named ARM. So for that purpose we have to again write compiler for ARM. Again we have to write for this, so the Objective C to the ARM conversion. So total how many compiler we are writing? 3 plus 3, 6 compiler. So if, let us, the language I am calling as front end, and the language which I am calling here as front end, and the hardware which I'm providing support, we are calling it as backend. So front end consists of how many stages, or how many, if there are like 3 front end, right? C, C++, and Objective C. So let us call as 3, and backend as 2. Then how many compiler we are writing? 3 cross 2 equal to 6. Now if let us suppose a new hardware will be coming, so 2 plus 1 will become 3, and total we have to write 9 compilers, and every time we must be doing the redundant work. So this is the before LLVM, the flow was there. This was the before LLVM, the flow. Before LLVM, the flow. So basically we have a high level language. Sorry for the inconvenience. So I'm starting my season from the scratch due to some network glitch and other thing. I was not able to having some trouble here in network. So let me initiate my from the scratch. I'm audible. I'm audible. As Aditya mentioned, I'm audible. So let me start. So I'm starting again from the scratch, and we're talking here about LLV. So let me quickly ramp up what I want to mention here. If you see what LLM stand for from the website of the LLVM, it is low level virtual machine. But is it low level virtual machine? No, it's more than that. Then what LLVM is? Is LLVM is a compiler or it's a framework? We can't say a compiler because compiler role is very simple and straightforward. What is the role of compiler? Compiler take Compiler take .i file as input and generate .s file and do multiple things like semantically verify where your assembly file and source code are correct or not. Then second is that validation of your source assembly. Another thing. Third is that parsing and errors giving. And fourth thing is that it's also optimize the code. So these are the four basic work of the compiler. But LLVM is more than that. LLVM provide you the complete infra. So what that infra will do, it will analyze your code, it will optimize, it transform during compile time, link time, and runtime. This runtime, when I say done by the, I mean by the PGU and other way, which I will discuss in upcoming and later way. So these are the completely work of the LLVM. So what we can say is LLVM is a compiler? No, it's not. Then what is LLVM is? LLVM is a framework. What is LLVM? LLVM is a framework. What that framework is? If we are talking about LLM is a framework, then which kind of framework it is? LLVM is a compiler framework. What that framework is designed to do? It enable analysis and optimization throughout a program life. What here I mean by program life? Let's understand that. When I see what is a program life, it simply means in LLVM context, if simply doesn't in LLVM context, what I'm telling you is that LLVM, first of all, what it is does, if I'm talking about the design perspective of the LLVM first generate one intermediate representation. What that IR will do, that IR is the soul of the LLVM. Everything happens in IR. Your source code get converted into IR, then all the things, nasty things happen on IR, and you get what? A assembly file, and from there exe. So during the phase in LLVM, your source code exists in the IR format is called as program life. So in LLVM terminology, when I say program life, during the whole duration, when your program exists in IR format is called as program life. But it's not actually correct, but you can think like that. When LLVM say program life, it means that LLVM is not just a compiler which runs and finishes once. What it does, it's a system that keep understanding and improving a program through its life, including at different stages, such as what? Compile time, link time, run time, and when the program is ideal. So note the entire period during which a program exists in LLVM for IR form can still be analyzed or transformed. So what is a program lifetime here when LLVM say? In LLM terminology, when we say program life, then there are four way of program life we see. We see compile time, link time, and runtime. Together, how much time they are, what program is live, we call as program life. And even the time when program is ideal. So this is the complete what program time I fear mean. If again I go to the definition, what is LLVM? LLVM is a framework. Which framework? Compiler framework. Which what it does do? It enable analysis and optimization throughout a program lifetime. So that we understood what program lifetime is. Now let's understand. Now let's see before LLVM flow. Before LLVM came in the compiler domain, I think ideally it came around, the design was came around 2000. Then from there 2000, Apple was the first company to enable Clang around 2006. Then from there 2006 onwards, LLVM was well-known player in the market. So first step was taken by the Clang to, even Apple created the Clang language to use LLVM as their framework. So there was, well, I will create one more video on that if you are interested in that history, little bit about LLVM, which will be beneficial not in the technical context but understanding the complete framework, why it exists and why it came. So before LLVM, how was the flow? Let's see. When I say before LLVM, think of like I will use three terminology I will use three term always. Which are the three terms? First one is that front end, and second one is the back end. When I say front end here, it means that any if you think of any coding language like C, C++, that I will call as front end. And when I say backend, then here backend simply means any new hardware. Hardware means your it can be x86, it can be ARM, it can be your RISC-V, it can be PowerPC or anything. So these two I will be going to use. Front end as a replication of coding language, and backend means new hardware. So let's start a discussion. So before LLVM comes, what happened? Let us suppose I am a company or institute whose role is what? We want to write a new programming language for our particular hardware H1. Let us suppose this is one hardware for the coding programming language P1. What we will do? We will follow all the compiler stages and we will create a H1. Now let us suppose we now want to shift our domain and we have created new more language and I want to work on that particular language. For that purpose, again, I will create a new front coding language as P2 as a front end, and again we will write for the backend for H1. Now let us suppose I created one more language as P3. Then again I have to write for H1. So how many compiler I am writing? One, two, three. When I am saying how many compiler we are writing, it simply means that we take the source, we take the .i file, and from there we generate the assembly code which the hardware understand. That is the role of here 1 2 3 I mentioned. Now let us suppose, say, change the scenario. Now our hardware got one upgradation, so I will update it here now. But let us suppose from H1 now we need a new hardware. A new hardware H2 came. This H2 should also support these three programming languages. So again, what we have to write? We have to write the front end for all these three. So total, how many compiler we are writing? Six. So three front end, two back end, then number of hardware becoming six. If I will increase front end by one and hardware by one, back end by one, then total how many compiler we have to write? 4 into 3 is equal to 12. So if you see, but multiple place we have to do redundant work. Maybe the same thing code I design can use there. So we have total, let us suppose m front end and n back end. Then we have to write m cross n compiler. So you can just imagine how it will you can think how many work we have to do. And in this scenario we have to write do parsing, then after parsing what we have to do. If you have understand of the compiler work in six phases, right? Lexical, then syntax, then semantics, then from there optimization, then three code generation, then code gen. These are the complete we have to do repeat for each cases. So here repetitive work will be more. This is was the design before LLVM. So let's see in detail. So before LLVM, we have a high-level language and we are converting it to binary or the assembly language. Then we get preprocessor from a compiler to assembler, then linker. Here, if we are mostly are interested in designing this compiler. So limitation before LLM, what was there? Every compiler used to generate what intermediate representation. We will tell you why we generate, but they were temporary and internal. As soon as the compiler work used to that, they used to get deleted even inside the source code, not just on your hard RAM or on your hard disk. There were no persistent intermediate representation like before LLVM. The great compilers exist during that time was GCC. GCC used to have two. GC has two uh, intermediate representation, RTL and Gimple, but they were not consistent across. Third, hard to optimize across module, or modules means whole source code is difficult to optimize. And there were no link time. Like we are only focusing on what compile time, we were not focusing on link time. We can also optimize at the duration. Before LLVM, link time optimization was not there. And after that, no runtime optimization. Here no runtime optimization was there. So this was again taken care by the LLVM. So after LLVM, what things change? Let's see. So after LLVM, what happened? Before going to LLVM, people what they thought in industry. Let us suppose we want to convert this particular source code into assembly. And that's the role of compiler. So instead of directly converting to the assembly, why not first create one intermediate representation which will be neither too abstract at source code, neither too low level as assembly. It will be in between two. So what benefit we will get? Let's see due to this decision. So let's take our previous example. We have a P1 language, then I am converting into IR, and then I am converting it to what? x86 backend. Or let us suppose here H1 backend. Now let us suppose we are now created new programming language as P2, then we have to translate to the IR. Now if a new here, if let us suppose here what new hardware is coming H2, then also we don't have to worry much about anything. We just have to write IR for this. So here how many time I am writing compiler? 1, 2, 3, 4. Now P3 will come, then I have to write this translation once and this translation two. 5, 6. So there are like total 3 front end and 3 back end. Then how is due to IR? we have to write 3 plus 3 equals to 6 compiler. But if we don't create IR, then we have to write 3 cross 3 equals to 9 compiler. Let us suppose now this for small. Let us suppose now if we have a 10 front end and 20 hard back end, then total will be we have to create 30 compiler if we are not generating any intermediate representation. If we are generating any intermediate representation, we have to create a 30 IR. But if we are not generating any 30 any intermediate representation, then just think we have to write 200 times same code redundantly. We have to write 200 compilers. Here we have to write just 30 compilers. You can see the difference of the IR, why the IR is important. So after LLVM, the flow of the compiler change how we have a source code. That source code get converted into IR, and that from IR we are able to generate the assembly. And here the flow is not that as much simple. I'm just we are giving an abstract level an idea. Due to this IR generation, what is happening, we don't have to do redundant work, and compiler people work has decreased drastically. You can just think of how many backend, if I can give you 10 backends on the name, and different companies backend always also their hardware get upgrade every time in new release, and C++ features also get released. So just think how many your workload has been decreased just due to this IR decision and common IR. And one more thing has happened, because earlier compiler only used to think about compile time optimization, but after the LLVM came, they were also thinking about link time optimization, runtime optimization, and re-optimization from bitcode, right? So if you see the flow, we have a source code, then from source code we generated LLVM IR, and this from LLVM IR there are two types of different optimization which compiler designer has done. One target dependent, target independent, which we'll talk in later what is difference between them. But in simple term you can understand as target independent optimization means, let us suppose you have a hardware, right? You don't, there may be some hardware related features which different hardware may be supporting but not yours, so you can't implement all the optimization on same all hardware. So whatever optimization which are independent of the hardware, they are only dependent on the source code, we used to keep in target independent. Then from there we get a code generate. From there we again optimize target dependence. Then we have a code generation, we generate the assembly code, and from where instruction selection, then target, then all these things happens. It's a very huge pipeline which I will explain in other lectures. Just for but be briefly you can get an idea how the pipeline of the compiler has been changed just due to the LLVM. But before understanding this pipeline, you must have an idea that which we'll see in LLVM designing class. After this we will take that. So before LLVM, compiler mixed everything, front end, middle and back end tightly. They were tightly coupled. After LLVM, the front end job, middle end job, and back end job was little bit more tight, less tightly coupled, or you can say less tightly coupled. Tightly coupled means not much more depend on each other. They can be worked in a modular way. So LLVM keep persistence higher. Therefore, optimization is not limited to compile time. So optimization move from compile time to link time optimization, runtime, and re-optimizing from the bit code. So the 5 core capabilities of the LLVM are there, which no other compiler have. Is first is the persistence programming information. What does it mean? The persistent program information is that I told you, right? LLVM generate the IR, and this IR information is taken care till the end of the program cycle. So LLVM keep notation of this IR every time. The it preserves the LLVM IR formation. When I say offline code generation means you are able to generate the binary, right? And third, user based profile optimization. We used to, depending upon what user requirement is used, we used to profile it and optimize it, which none of the other compilers providing during that time. Then transparent runtime model. So let us suppose if we talk about JVM. What is JVM? Java Virtual Machine. It can't run C++ and other thing. So it has a not that much transparency. So LLVM has removed that transparency and created a transparent virtual machine. and it also created a uniform whole program compilation. It simply means, if we talk about the point 1, 3, and 5, so during none of the compiler, this 1, 3, and 5, none of the compiler during that time used to provide. But some compiler may have 2 and 5, but all the three, all these 5 points during that time, none of the compiler have. So LLVM has solved that problem. So also, before going, what LLM does not do, it does not guarantee your type safety, memory safety, and language interpolability. It does not impose any particular runtime and semantic of your program. It does not represent high level feature directly. So it doesn't. So for this, what LLM does not do, for that purpose, I need to take more session, because for each topic what I mentioned here does not like guarantee type safety, memory safety, and language interpolability. Can create a separate class for that. But just keep in your mind, in upcoming lecture all these things will be clear how why it is not able to do. So the no notion of high level constructs such as class, inheritance, or exception handling semantics. So the LLVM architecture, in simple way, we can see LLVM architecture, front end, IR, and then back end. So design of LLVM compiler framework, we will see it in upcoming lecture. Till that time, you can just go through LLVM documentation from